All right, so let's pick it up from where we left. So remember we had talked about the identity and how the identity equals 1. Or not equals 1, but explain the role of 1. And one thing that identities satisfy is that if you have, say, A and then A inverse, when you multiply it, then you do A inverse times A, that should give you your identity. Let's call it little I, if you will. In our case was capital I, is what we're calling it. Let me remove that box, annoying box there. And you have an example of that. So for example, for when the operation is multiplication into real numbers, you know that 2, then that 2 inverse, the multiplicative inverse, is just a reciprocal, and that satisfies the product that 1/2 times 2 equals 2 times 1/2. The product in reals is commutative, so I don't have to write the whole thing, but yeah, I'm gonna write it anyways, is equal to 1. And we use this whenever we wanted to solve an equation, because if we had an equation of the form ax equals b, a linear equation I should say, then if we put it in this form, then whenever we multiply times the multiplicative inverse or the reciprocal, we would obtain that x was that number, whatever, b over a, if you will. So we solved equations in that form. Excuse me. However, that is not true in general for matrices. We can check that I can have, for example, this would be playing the role A, and this could be the role of X, and then this would be the role of A again, and this would be the role of Y. If AX equals AY and you divide both sides by A, quote unquote, then you should get that X is equal to Y. But you can clearly see that X 2, 1, 4, 2 is not equal to Y 1, 2, 5, 1. And you can check that these two products are going to give you this. And you say, oh, there seems to be a problem with mathematics. We broke mathematics apparently, but it's not quite the case. What happens is this matrix A will happen to be sort of like the role that 0 plays in the real numbers. The only number that has no reciprocal in the real numbers is 0. You know, you cannot divide by 0. Remember that. So if you do 1 over 0, well, that's not possible. Unless you're Chuck Norris, as we have established. However, this A, even though it's not 0, it's 1, 1, 1, 1, it will sort of be like a 0 for us. In that it doesn't have an inverse or a reciprocal, but in our case it's an inverse because there's the reciprocal we use for real numbers. All right, so now if a matrix is such, so if A is a square matrix, for which a matrix A inverse exists and it satisfies the following equalities, where I represents the identity, then we say the matrix A is invertible. And the matrix A to negative 1 is called the inverse of A. If no such matrix A to negative 1 exists, the matrix is said to be non-invertible. So that is going to be what we're going to use as our definition. That's going to be the definition of an invertible matrix. So how do we know when whether a matrix is invertible or not? That's going to be an interesting question that was going to take us a little bit of time to determine. However, there's some things that we can prove without really knowing yet how to determine an inverse. So that is what they want to do. So the theorem is that if a matrix A is invertible, so we don't know whether it is or not, but if it is, then the inverse is unique. And then I start off the proof here. So if A is a square matrix, sorry, if it is a square matrix and it is invertible, so let's assume there's more than one inverse, and so label them as A inverse B. We didn't really need to do it by contradiction. So let's take a look at what happens. So by virtue of A being invertible, we can start with A inverse, and we can just write it as A inverse times the identity, right? I mean, the identity satisfies that whenever you multiply anything times it, you're going to get that anything back. And then since A is its own inverse, sorry, A is its own inverse, what am I saying? Since A is invertible, sorry about that, then you can write the identity is A times A inverse, right? But I don't like this inverse I'm using here, so I'm going to write it actually as A inverse times A times B. Why? Well, because B is also supposedly an inverse of A, so A times B is also the identity, so I'm going to write it like that. It's a little bit better because then I can use associativity of the matrix product and write it as A inverse A times B. And now I remember that A inverse A is also the identity, and I get the identity times B, and then I get that I times B, anything you multiply times the identity. Remember, this is a square matrix, so this same identity I multiply on the left, I get on the right. So no worries there, it's just I sub n, where the matrices are n by n, so no worries. And that is going to be equal to B. So, but if you look at both sides of the equation, B is funny. Actually, it's not funny. That B looked like what my mom used to write, draw as a heart. So instead of drawing a heart, she would do this. And so the first time she sent a card to my wife, she wrote this heart, uh, and then she wrote mom. And of course, my handwriting is not identical, but so my wife asked me, "So who's B?" Like, no, that's a heart. She loves you. Anyway, so A inverse equals B when you look at both sides of the equation. So that B was a nice B. It was a heart because we heart math. Yeah, no, never mind. I took it too far. So anyways, A inverse equals B. So we didn't really need to assume a contradiction, but if you have supposedly two inverses, you can determine that they're the same. So it's not two, it's just one. All right. So the condition of the matrix being not equal to 0 is not sufficient for a matrix to be invertible. I mean, with the experience we have from real numbers, we could assume, oh, well, as long as the matrix is not equal to 0, then it is invertible, but that is not the case. So we have to figure out what would be a necessary and sufficient condition for invertibility for a 2 by 2 matrix. So we actually can compute the formula. So you can do this, and I used to have an exercise, but people would get really confused. But if you have the matrix A, B, C, D, and then you multiply it times the matrix A, X, Y, Z, W, and you force that to be equal to the identity, so 1, 0, 0, 1, then you end up with a system of four equations on four variables, because A, B, C, D would be known. And when you solve it, you get this formula here for the inverse. It's a lot of computation and people would get a little confused, so I don't add that as an exercise anymore, but I give you the formula. So the formula is that, so if you have a matrix of the form A, B, C, D, the inverse would be given by this formula. And I'm being obtuse. I'm not saying the whole thing because I want you to think about, before I tell you everything is written, but I want you to think about what happens when AD minus BC is equal to 0. Well, you get 1 over 0, and as we said before, you cannot divide by 0 unless you're Chuck Norris, and you're not. So you have here a problem, so the matrix is invertible if and only if AD minus BC is not equal to 0. And if that's the case, then you have that the inverse is given by this formula. I'm going to skip this proof, but really all you would have to do is multiply out the matrix A, which is A, B, C, D, E, F, G. No, just A, B, C, D, times A inverse, which is going to be 1 over AD. Goodness gracious, that was exciting. AD minus BC. I'm just writing the formula for A inverse that I have there, D, negative c, negative b, a, and then you would have to check. You move this coefficient. This is just a number. Don't freak out. You just move it to the front. You multiply these two matrices you know how to do, and then distribute this fraction into each, or you do the scalar multiplication. Really, that's what you'd be doing. But you distribute it for each one of the entries. I'm gonna say it the same way because it's really what you're doing or what's happening. And then you end up with the identity, and you'd have to verify that. And I did here A inverse, and then you have to do A inverse A. And so it's tedious, but that formula is going to work. So let's take a look at a few examples. And that formula I do want you to remember because it's quite useful. So let's compute a few inverses to determine whether the matrix is invertible or not invertible. So let's start by computing AD minus BC. AD minus BC is going to be A, which is 1, times D, which is 3. A, B, C, D, right? So 3 minus B, which is this guy here, negative 3, times 2. And then you say that's going to be equal to 3. And then minus negative plus 6, which is 9. So you get a 1/9. And then the formula for your inverse is you swap the diagonals. I mean, you can look it up. It's D and then A, but this is the best way to remember it. Swap the diagonals. So 3, 1. And then put negatives in front of the off diagonals. And this formula, please, 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 only works for 2 by 2 because some people get creative. And they say, well, I can do it for 2 by 2, I can do it for 3 by 3 and 4 by 4 and whatever else you want, but that's not the case. So um so yeah, and I don't even know how it works in their mind, how it works for 3 by 3 and what kind of change you do in the diagonal. I don't know, but people do think that it works, and it doesn't. So just be mindful. So this one was invertible. We got the inverse. You could do the scalar multiplication and get the 1/9 to multiply each entry, but I like it there because I ended up with 1/3, 1/3, negative 2/9, 1/9. Too many numbers in one matrix. I'll leave the 1/9 out there. But now this one though, if you do the AD minus BC, which is going to be called the determinant, by the way. But right now it's the AD minus BC. Sounds almost like a rock and roll band. Anyway, I don't know. 2 by 2 AD. And then minus 4 times 1. So that's 4 minus 4. That 4 is funky. Oh well. It is all 0 anyway. So since it's 0, this matrix you cannot write 1 over 0. So it's non-invertible. Or B inverse does not exist, if you will. It's not invertible. So now, going back to equations. If you have an equation of the form ax equals b, this x and b lost their uppercases, their lower cases, because x is going to be a vector, which is going to be, if a is an m by n, for the matrix for the multiplication to be possible, these two guys have to match. So that has to be an n by 1, because it's going to be a vector. So n by 1 is n rows 1 column. So it's going to be a column vector. X is a column vector with n entries, an n tuple, or what we call Rn. So X is a vector in Rn. And A, since A is m by n, then the result B, when you pre-multiply X with A, remember the order does matter here. So A times X gives you B. B is going to be an m by 1 vector. So again, m rows and 1 column. So it's going to be a vector in Rm. So that equation, if you have this equation and A happens to be invertible, what I can do is I can multiply both sides of this equation by A inverse as we did with numbers. However, I have to be very careful to multiply it on the left. I cannot say now B A inverse. No, 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 no. You're multiplying on the left. So you gotta be careful and always multiply on the same side of the equation. That's one thing because matrix multiplication is not commutative. So you have to be careful. Now, with that, I get that this is the identity times X. That's identity times anything is anything. And then this is gonna be A inverse B, and so I should just write this as the vector X. So I can solve that equation automatically by multiplying times the inverse. If I had a way to compute inverses, remember that only for 2 by 2 I know how to compute inverses at the moment. We will learn soon enough. So some properties of the inverse. The inverse of the inverse is the matrix itself, and the inverse satisfies the shoes and socks principle or property if you want. Shoes and socks. I really like the name. I had never heard it until I moved to the US, but I really like it. It's quite appropriate actually. Shoes and socks. I don't know if that end works there. Whatever. You just turn it into a first end. There you go. Shoes and socks, as I said. All right. So let's go ahead and prove this real quick. So I kind of don't want to do this one. Let's do both. Okay, fine. How much more do I have? Let me pause this. Oh, you unlucky souls. That's the last thing for the class. For today's lecture, so I will prove him. You see, if I had another example, I'd be like, nah, you know what? Never mind. But too bad. All right, so let's go ahead and take a look at this. A inverse. Um, inverse. No, A inverse times, let's do this. A inverse. Inverse is 1, right? The identity. Because I'm just grabbing the inverse of the inverse and I'm multiplying it times the inverse. I mean, just think about this A inverse as the matrix B. Something B times B inverse, that has to be the identity. But on the other hand, A inverse times A is equal to the identity. And if I write it in the opposite order, the same is true. But I proved that the inverse of a matrix is unique. So these two guys have to be the same because the inverse is unique, and these equations and the reverse as well, but I'm not going to write them, establish that A is the same as the inverse inverse. So yeah, pretty straightforward. But the first time you see it, it's a little bit messes with your brain. So the other one is just checking that A, goodness, that A, I don't know why this thing is doing something weird. So I'll just keep going with the punches. So AB times this other matrix, B inverse A inverse, is going to be equal to A, and I'm going to associate it like this. B inverse, the multiplication is associative, so I can reorganize it. The term in the middle is the identity, because B times B inverse is the identity. All these are invertible, remember? So it's going to be A inverse. And there's an identity in the middle, but when you multiply it either times A or times A inverse, it's going to be just A or A inverse, so it'll go away. I'm going to skip that. And then that's going to give me the identity. So what that tells me, now I can do it in the opposite order as well. So A, or opposite order, I said B inverse, A inverse times AB. You do the same thing. You see the A's in the middle will cancel, and then the B's will cancel, and you're going to get the identity back. This tells me then, by the uniqueness of the inverse, that this matrix in parentheses happens to be the inverse of this product, which is written as AB inverse is B inverse times A inverse. But this is the shoes and socks principle. Why? Because whenever you're going to put your socks on, you put your socks on first, on your shoes, on your feet, and then you put your shoes on top of it. So think about the operation of putting your your socks on being B. So you put your socks on, you do B first, then you put your shoes on, which is A. When you want to take your shoes and your socks off, you don't start taking off your socks. You start first by taking off your shoes. You take your shoes off first, and then you take your socks off first. I'm reading from right to left because that's how you apply operations. That's why it's called shoes and socks, because when you're going to do the inverse, you have to do it in the opposite order. And that's also true, for example, when you're doing the antiderivative of x to the n, like the famous power rule. Oh, you see, I told you in class that you wouldn't need calc 2. Well, this is calc 1, really. I remember the way we did it was you added 1 to the exponent, and then you divided, sorry, by that new exponent, and of course your plus c, but that's not what we're talking about right now. What we're talking about is this formula. But why is that? Well, if you think about, you're undoing the derivative, and in the derivative, the first thing you did was drop the exponent, and then you subtracted 1 from the exponent. So the first thing you want to undo is the last thing you did. The last thing you did was subtracting 1 from the exponent. That's why now you're adding 1 to the exponent, because you're undoing that first. The first thing you did, which is the second thing we want to undo, is multiplying times exponent. So that's why we're dividing by the new exponent now. So you see the shoes and socks principle is right there as well. So it'll occur if you start thinking about it. A lot of the things, when you do two things sequentially to undo it, I mean pretty much everything, you gotta undo the second one first and then the first one. So there you go. You got to learn about the shoes and socks principle. Probably you thought about it and knew it, but you never really uh, wrote it down, I suppose. Anyways, that's that for today, guys. Thank you for your patience this week. Thank you for, um, um, you know, not being too sad that we had to cancel class. I guess nobody was sad. Well, I am sad because I'm here at night creating videos. Oh well. I also had COVID, so not a great week. But we'll do great next week. So see you guys in class, and barring anything weird. But um, have a great weekend. Enjoy the video, and see you next week.